Log on, tune in, find out. Another good idea from Cambridge.
First, I would like to thank Angela and the other organizers for the invitation, Jack for the introduction, and NSF for the support. So Russell is here, so I have to thank. So this is a joint work with my student Shanba, who will be graduating soon. So I think back to the deterministic simulations. Okay, so there's no need to talk more about the GP model. We have seen it many times. With a constant mean, it can also be called the ordinary Kriging. Yeah, so when we have data from a computer experiment, we can obtain the predictor, which is a very simple form. And so the question I am trying to answer here is, can we improve that prediction? And another nice thing about the Kriging approach is that we can directly get a confidence prediction interval. So that's one nice feature about this approach. But again, I am trying to see whether we can improve that prediction interval. And so when trying to improve a method, so we need to look at its assumptions. So these are the assumptions behind that GP model: constant mean, constant variance, stationary correlation function, and Gaussian distribution. So we can try to challenge each of those assumptions and try to improve it. And in this particular work, I'm going to focus on the first two, the constant mean assumption by proposing a better mean model, and the constant variance assumption by proposing a better variance model. Let's see if it is going to improve or not. Before getting into that work, I want to just touch on two earlier methods that I have worked on, called limit Kriging and blind Kriging, because those ideas motivated for this work. So you can see that progression. But there are several other approaches which I will not talk about. So some of the others are here, like Dave Higdon is here, so you can ask him for the details. So here is a limit Kriging idea. So we have a function and some points, and the red one is the fitted model, the ordinary Kriging model. Okay. Just to see the idea more clearly, I am going to use a slightly bad value of the correlation parameter. Okay, the previous one is the optimized value. So if I plug in a somewhat a poor value, you can see that those predictions are pulled towards the mean. So now let's say, suppose we want to improve the prediction in this region. So we can try to put the mean somewhere here, then you will see that that region got improved. But the other region got much worse. Okay. So the idea in limit Kriging is to change that mean where we want to predict. Okay. So keep changing that mean wherever we want to predict, so that that region will get improved. So that I did in a recursive form. With some predictor, you plug in that value, get the new value, and recursively, if we do that, at the limit, it will tend to this one, solving that we get a very simple predictor, which I call the limit Kriging. So you can see in that with the worst value of theta also, the green one is the limit Kriging. It works better than the ordinary Kriging. So that's one attempt in trying to improve the ordinary Kriging prediction. Another idea is to use a universal Kriging method, like a polynomial term with interactions and all. So instead of a constant mean, we are using a more elaborate linear regression model. So here I put a linear trend here. So now even with that worst value of theta, the green will be pulled only towards that line. So predictions are better. I mean yeah. So then I try to work on this borehole model, fitted the linear terms, linear and quadratic terms, but the predictions are much worse. Okay. Okay. The ordinary kriging is doing much better. So even after adding the linear main effects and quadratic main effects, things are getting bad. But then I found out that if you do a variable selection and put only the important ones in that mean model, things can get better. Okay. So, so that's the idea of blind kriging, to do a variable selection also along with the kriging. So again, the prediction can improve. But this variable selection, later I found it's to be very unstable, and sometimes in a very complex response surface, it's not easy to capture the global trend, and so not always successful, the blind kriging. Here is an example. So this is an example from this paper. So here is the ordinary kriging prediction. So here I am using the best value of theta, okay, the optimized value. This is the best we can get using an ordinary kriging, and the prediction is not very good. You can see it's pulled towards the mean. If we reduce that correlation parameter, this side will get improved, but this will get very bad. So this is the best you can get. Now, if I try to apply blind kriging, putting a linear trend and all, it's getting worse only. Okay. Now some regions will get improved, but the other region will go bad because it has a much more complex shape. So then we thought of why not use another kriging as to capture the global trend. So it's like putting two Gaussian process model instead of one. So one is a global for global trend and the other for the local trend. And the solution is very easy because that reduces to another Gaussian process model with this as the covariance function. So it's easy to obtain the predictor, confidence intervals, everything. And you can see we can write it as the predictor can be split into two parts, a global trend predictor and a local trend predictor. So this is related to that blind kriging. Instead of a linear regression model here, we are having another kriging model. So here is that global trend. Okay, that's the red one. And now once I add the local trend to it, it's very good. So that blue is the coupled Gaussian process predictor, which is very close to the true one. So the nice thing about it is, that using a kriging predictor for the global part, it really captures that trend very well, and therefore it improves. You can see it's still going back to that red one, but it's not that bad, because it already captures that major trend. Has some connections with the nugget kriging predictor. If you assume, say, 0 correlations for the local model, so it becomes I, and so this is the predictor. So here is an example to illustrate that predictor. It's recently described in Gramasi and Lee paper. So these are the design points in red, and if you fit an ordinary kriging model, you can see the fit is not very good. Okay. Again, this is the best fit you can get from by a Gaussian process model. We searched over all possible values of the correlation parameter, and this is the best. So sometimes it behaves, in this way, in the opposite way. So Gramsci and Lee showed that for if you use a nugget predictor, actually the prediction error reduces. So this is the nugget predictor, it doesn't interpolate, so it's only an approximator. So but the overall prediction is much better than fitting a interpolating model. But now we can fit the two Gaussian process models. So instead of using a zero correlation for the second part, we can optimize and find the best correlation, and so that will look like this. So the red one is the global trend, which is like that Gramsci and Lee work. It's an approximator, but I can put another Gaussian process model over that to interpolate the observations, and the predictions are much better. The root mean square prediction error of this is again lower than the approximator. So I think this is a general result that give me any approximator, we can improve it by putting an interpolator over that for deterministic simulations. So so far I talked about how to improve the mean model. So let's see how to improve the variance model also. So here I am taking out that sigma from that local model, and I am trying to model that sigma also. So here there is no sigma. So how do we get such a model? Initially we thought, okay, let's put another Gaussian process model for maybe the log of the sigma square x, but it's computationally almost impossible to solve. It's very, very difficult to solve that. So there has to be a clever way of tackling this. So this is a very important question: how to obtain that in a feasible way. So what we did is we already have the global trend, get the residuals, and then do a smoothing. So that will be a kind of a so this can be considered as a local variance. So it captures that local variance of the function, and it's closely related to an idea that recently appeared in technometrics. So again, the prediction confidence intervals all are very simple because it reduces to a Gaussian process model. So it's very easy to obtain all these results and the prediction intervals. And again, we use the maximal likelihood estimate to get all these values. So the computationally it's much harder. So we have more parameters to optimize: correlation parameters in the global trend, correlation parameters in the local trend, and that variance ratio. And this one parameter B is also we introduced in the smoothing, because when B goes to 0, we wanted to get a constant variance. So it can reduce to a constant variance model. So we introduced one more parameter there. Otherwise, we use the global trend for B is equal to 1. So that parameter is also estimated through maximal likelihood. So here is an example. So again, a wiggly function with red as the point of observations, and here is the Gaussian process model, the blue one. And we can obtain the prediction interval. So it looks like that. Okay, so same thing we can do with the coupled Gaussian process model. So this is the prediction. Prediction in this case looks much the same as the Gaussian process model, but the prediction interval is completely different. Okay. The reason is you can see now here the variability is much larger, and here the variability is much smaller. So the intervals capture that property of the function because it uses the local variance, whereas in the Gaussian process model, the width is roughly the same. The reason is in Gaussian process model, if I go back to that formula, or yeah, so the prediction interval formula, if you remember, it only depends on the spacing between the points, and it doesn't depend on the y. All the y's are clubbed into just a sigma square, so that is used only for scaling. So it doesn't use a different variance at different points in the region. Whereas here, because of the sigma squared x in the formula, because of this, it captures that local variance, so that width changes depending on the y values also. So which I think is a very nice property. So again, coming back to the borehole example, 27 run orthogonal array, ordinary kriging was about 6, blind kriging slightly improved. So we also fitted the treed Gaussian process model. It's not doing very good in this particular example, but the coupled Gaussian process, you can see the prediction improvement is dramatic. It's less than half the root mean square prediction error. So when we increase the run size, again the coupled Gaussian process is doing better, but with a larger and larger run size, there is not much improvement. Okay. So I think when the data is sparse, this particular one really improves, and there is not much loss of prediction when there is more data. It's comparable. So this is another real example that we worked with some of the mechanical engineers at Georgia Tech on designing a heat exchanger. So they had actually two simulators. One runs very quickly using a finite difference method, and another very slow. But I am going to use only that quick simulations to illustrate the method. So we used a orthogonal array based Latin hypercube design of Gaussian tank, 64 runs, 5 factors, and we had 14 test data. So this is the root mean square prediction error based on the 14 test data. So again, ordinary kriging, blind kriging, and CGP, you can see the improvement is very, very good. The more than 50% improvement. So I think I went very fast, but I think it's good for, because lunch is waiting for us. So in this talk I introduced the coupled Gaussian process and shown that it gives improved predictions and improved prediction intervals. Through several examples I demonstrated that, but I should point out its disadvantages as well. It's obtained at the expense of increased computations. Okay, so that's the price we need to pay for this improvement. And so the computations get very, very tough with the large data sets. So far we are able to use only small data sets to demonstrate the method. For large data sets, I think Ben Halland is going to give a talk tomorrow, so his idea would work much better. So yeah, with that I will stop. Thank you.
Lots of time for questions.
Yes, that's for me.
Yeah, okay, sorry. Okay, so you used this underlying model to begin with, and that's and for that you use some regularization. So I have two questions. First of all, do you constrain your parameter search so that you get a lot of regularization? That's the first question. The second one is maybe it would be nice to see a comparison between just that model that's a very aggressive regressor of the data and your new improved model.
Okay, which aggressive regressor of the data?
Sorry?
Which one? Comparison between?
Your just underlying term with the high degree of regularization and your model that's based on fitting on top of that as well. Because maybe you lack some generalization if you overfit.
So yeah, going back. Yeah, so here we had to apply some constraints, or we initially applied some constraints on the correlation parameters, like here we wanted a much more smoother global trend, so a smaller correlation parameter, and a more rough, so a larger correlation parameter. So that was initially we tried, but later, after introducing the variance model, there is no symmetry between these two terms. If there is no variance term, you can interchange and there is a symmetry there. But once that variance model is introduced, there was no symmetry. So I think we didn't use any constraints in our optimization.
You just allow there to be a regularization term in one and not in the other.
That's right. So you mean the regularization term, you mean this one?
Yeah.
Yeah. So it's only that ratio that matters. So it's some sigma square times tau square, only that ratio matters.
And so the second part of the question was, is the combined model does that definitely give better generalization than the global model?
Yes, always. Yeah. So yeah, I think that point is very clear from this picture. You can always try to improve that approximator by putting one more, making
Although
it
your dotted line is closer to the solid red line in some areas than the blue line is.
Yeah, but overall, I think the prediction is improved. Yeah, yeah, I think possible to prove theoretically. At least because of the interpolation for a continuous function in some neighborhood, it will always improve.
More questions? Yes, please.
So you sort of hinted that this might be harder for bigger data sets.
Yes.
Might an idea be for your global trend model to not use all the data? If you're just trying to capture the trend, you could thin the data out a bit.
Yeah, that's Ben's idea. Use a subset to get a model, and the remaining subset to fit another model. So they add a multi-step Kriging model. So that's what they are working on. Yeah, that's a very neat idea.
May I add the comment that actually I like this about your approach, that it works especially for small data set. If you have a big data set, any of these Kriging models seems to work according to your numbers. So you don't need the improvement.
Yeah, but large dimension, very large data, maybe very sparse, So yeah, that area still it's a weakness. I think. Yeah.
More questions? Yes. No, you.
If I understand well, you have one parameter per data point for the variance now.
Yes.
And you fit that with the difference between the smooth process and the actual response.
Yes.
It's not a bit dangerous in the sense that if you, by chance, your smoother is close to the data, then you think that you have no error. And for strategies like expected improvement based algorithm, you might not come back again to that zone, even if you have indeed an uncertainty.
Yeah. You mean almost like interpolation?
Yeah. Yeah, but interpolation by chance.
Yeah, by chance. Yeah. We tried several examples and didn't come across that problem, but I see that could be a concern. But yeah, we never came across such an example, so we thought it's okay.
We could find a counter example, I guess.
Yeah, could be. Yeah. So then the idea will be to put some upper bound on B, so that it won't interpolate.
Maybe you might not have one estimate per point.
Yeah.
And do some kind of smoothing for the variance itself.
Smoothing for the variance, yeah, that's what is done here, right?
Right. But
yes.
At the very point you have exactly the S square, or
no. This is only a smoother, not an interpolator. Yeah.
Okay. Can you show slide with results for Borehole model.
Pardon me?
Results for Borehole model.
Oh, okay.
Okay. Can you say how much parameters did you estimate for each?
Yes,
Okay.
it's there are 8 factors, so 8 correlation parameters for the global trend, 8 for the local trend, 16, and then 2 more, so 18 parameters.
Does that answer the question?
For each method.
For
Each method, you said.
for each method separately, yeah. So ordinary kriging, it will be only 8 correlation parameters. For blind kriging, there was only 1 linear term, and this is what I said, 18 parameters. Yeah. So there is a big step, like 8 to 18.
Okay, more
But
questions?
Roshan, those are holdout predictions, right? That prediction error that you're showing us, right?
These prediction errors,
Yeah.
it's so this model is very simple, so we can generate as many data points as we want. So this is a real prediction error.
So in sort of sense, the degrees of freedom, if it was too much, it would already show up in the prediction error, right?
Yeah, that's right.
Since you brought this up, can I just ask about your TGP when you ran it? Sometimes the trees have trouble mixing. Did you? How long did you run those chains for?
Oh yeah,
Did you just use the default in the package, which is probably too small?
default in the package, I think.
Okay, so it's probably way too small to get good results. And
Yeah, maybe it can be fine-tuned, but Shan did all the computation. I didn't get into the details. Yeah.
The default is for like a one-dimensional problem.
Okay.
I have a question actually. In the beginning, you said there's 3 parameters: the mu, the sigma, and the zeta.
Yes.
And then you started playing with the mu,
And the
and they gave
sigma.
better result than the sigma. How about the final step, the zetas? You didn't touch that, did you?
No, I didn't touch that.
Are you afraid?
But let me point out the other work.
It gets more difficult. I understand that,
Yes,
right?
yes. But already there are several approaches on the covariance functions. You know, Dave has and many others. Yeah, so they have proposed a non-stationary covariance functions.
Okay.
Any thoughts about minimum number of runs in order to find this method effective?
Yeah, we did not do any such simulations, but I guess there are 2p plus 2 parameters, so it should be much more than that.
Yeah.
Yeah,
Well, 27 isn't that much more than
18. Yeah,
Yeah, so that's why I was
but it
wondering.
still worked. Yeah,
Right, it still worked. That
still
was,
worked. Yeah.
that was what prompted the question.
Okay. Everybody ready for the photo shoot? Okay, then let's.